So thank you, Son, for joining this initiative. So I am Naveen Kumar, working with Irish Bioeconomy Foundation as the European project manager. And here we have an initiative with our European projects, Rural Bio and Primed, to share the knowledge to the community. So I would just give you a bit of introduction of the project. So Rural Bio-op is an EU-funded project under Horizon Europe that aim to support the development of regional bioeconomy hubs in rural areas by fostering innovation, collaboration, and investment in biogas solutions. And this project also provides tailored capacity building, network, and knowledge sharing opportunities to enhance bioeconomic initiative across the Europe. And then another project is Prime, which is IBF leading an EU-funded project under Horizon Europe, again focused on developing multi-actor ecosystem to promote sustainability, primary production-based bioeconomies in rural and coastal regions across the Europe. The project aims to enhance circular bioeconomy value chains by integrating digital tools, stakeholder engagement, and policy recommendation to drive innovation and sustainable growth. So these are the two projects, and for that we are organizing this series of webinars so we can get an idea of what are the technologies being used in the industries and share it to the community to get them a grasp of the technology. So thank you, John. Thank you, Son, once again for joining this, and I would let you introduce yourself and then we can start with the slides.
Hi, Naveen. Thank you very for that introduction. So my name is Sean O'Grady. I am the Chief Operation Officer of the Irish Bioeconomy Foundation that's based here in Lachine in Tipperary. I'm also Director of Premier Green Energy, where Premier Green Energy is a technology supplier, particularly to kind of the for climate technology solution providers is something there that Premier Green Energy will be kind of targeting. So it's not just about pyrolysis or advanced thermal treatment. It's about the wider bioeconomy applications and the opportunity for refining, whether it be kind of thermal biorefining or biological biorefining activities. So Premier Green Energy kind of covers a multitude of activities there in that whole circular bioeconomy, which I think is one of the reasons there why I suppose we're having this discussion today, is to explore some of those technology solutions and some of those aspects there that Premier Green Energy are active in. And that ties in quite nicely then with my IBF role in terms of the operations officer in Lachine, is to be able to look at pilot scale development and upscaling of technologies, coming from laboratories, coming from research institutes, looking to deploy technology into that whole circular bioeconomy area.
Thank you very much, Son, for the introduction and giving me the background of what you do and the need of these things. So I will let you go through your slides and talk about the technologies you're using currently and which you find it relevant. I will switch off my camera and let you speak on your slides. And then once you finish, we will have a follow-up questions.
Perfect. Excellent. Thanks for that, Naveen. So I'll just give a general overview of Premier Green Energy, what we're about, and maybe some of the areas there that have interest. And specifically in this scenario here, I'm going to kind of focus in maybe on advanced thermal treatment. And with the slide here in front of us there, I'm just kind of focusing a little bit on pyrolysis. I don't want to get too heavy into technical detail, but I just want to give you a good flavor of the opportunities and the systems relating to advanced thermal treatment and how that relates back then to kind of the overall bioeconomy sector. So with that in mind, this current slide here is kind of demonstrating thermal treatment principles across the full spectrum of waste energy and incineration and combustion activities. So typically Premier Green Energy likes to focus within, on the left-hand side of the screen, is a pyrolysis system where there is no air, no combustion within a kind of a furnace application. Sometimes there's challenges regarding where is the demarcation between pyrolysis and gasification, and trying to understand. So in principle, pyrolysis is where there's an intention to avoid air ingress into a system, and where you're trying to achieve pure pyrolysis conditions in the absence of air. Whereas gasification typically is where there is partial air, and forms of incomplete combustion. So again, we're always trying to maintain sub-stoichiometric conditions to ensure that you're operating with that process or gasification type area. Incineration is probably at the other end of the spectrum from in that overall scheme, that it's usually excess air. So there's more air in there than what's actually needed to actually combust certain kind of feedstock and certain materials. So again, pyrolysis is an area that PG is very much focused on, and is an area where they have a lot of experience gained over the years. So within that in mind, I suppose one specific technology here that they've kind of developed over time was a kind of Prima 300 or 3000, I beg your pardon. And that's where it's kind of an advanced thermal treatment system, again, where you can present a range of feedstock. So it's not just a biomass, or it's not just maybe virgin materials. What you're looking at here is a range of feedstocks that's quite flexible, or it can be a blended nature of feedstocks. It can include anything from general waste, biomass, farm agri residues, and it needs to be presented in a certain manner, and that's an important aspect to kind of pyrolysis, and that's one of the major differentiations between pyrolysis and perhaps mass burn incineration applications. Pyrolysis needs the material to be prepared in advance. It needs to have a certain presented in a certain format. Whereas mass burn incineration, typically it's a black bag rubbish scenarios which are readily fed into the incineration application. Whereas with pyrolysis, it's a little bit more selective. It needs to be kind of pre-treated in some instance. So again, ideally those black bags that would be typically presented into incineration process, these will be ripped open. You take out the high value products, so maybe plastic components, metals, ceramics, stones, anything there that might have a value in terms of a commodity or as an aggregate that can be utilized. So they are typically extracted, and what you're left with then is a residual fraction that would typically then maybe go into an incineration or onto a landfill application. That's the feedstock then that we presented to a pyrolysis system. So at that point in time, it's usually shredded. It's important there from a heat transfer perspective to ensure that the actual material is presented in a format that can be readily decomposed and readily reformed within the actual pyrolysis reactor. So this is where, again, the material is typically shredded. Sometimes there might be a bit of moisture reduction by putting it through a dryer, but also you're taking out, removing a lot of the metal, glass fragments, ceramic fragments are in there, and you're left with this kind of flock material, typically referred to as a refuse-derived material, RDF, or sometimes referred to as a solid recovered fuel, SRF. So for the purpose of this here, I'll just kind of refer to there as an RDF material. So that RDF material is fed then into a pyrolysis reactor. Typically a pyrolysis reactor, again, you're operating in the absence of air. You're operating at relatively high temperatures, somewhere between 600 and maybe 700, 750 degrees centigrade. And you're exposing that material for a period of time. So again, that can range from seconds to minutes or tens of minutes. So I know from a primary green energy perspective, typically we're looking at residence time in around about 10, 15 minutes, depending on the rotary kiln design, and typically operating around 700 degrees. And under those sort of conditions, you're maximizing your gas potential within that. You're ensuring that the carbon that you're generating or the char that you're generating out the back end is completely devoid of any volatile fractions within that. So you've absolutely taken out as much volatiles in the form of a syngas as is possible. So the primary green energy system is specifically a rotary kiln design. Within that rotary kiln, you have a certain furniture and systems within that allows the char to be entered on one end and to be extracted on the other, and where you can control the temperature profile and control the residence time of that kind of char component to ensure that you've optimized that process and extracted all those volatiles. So the char component is quite an interesting, very versatile product. When it's being derived from waste, it does have certain restrictions for what you can be used for. But when it's coming from a virgin biomass material, you have increased versatility is what that biochar can be used for, and it's a very versatile product. Can be used for filtration purposes. It can be used as a kind of soil amendment material. It can be used as a biocoal or as a peat substitute, for combustion or fuel applications. So again, it's an extremely versatile product, and again, char and carbon is a very important aspect of this. So you're extracting this carbon pre-combustion of any of the syngas. So it's an important aspect to kind of where you can actually physically sequester this actual carbon product. The syngas then is another byproduct of, I suppose, a char production, or if you like, the char is a byproduct of the syngas generation. But either way, what effectively is happening here is you're splitting the feedstock into kind of two distinct components and commodities, one being that syngas and the other is the char. The syngas from a utilization perspective is again quite a versatile energy form. It is obviously a gaseous product. It is consists of carbon monoxide, hydrogen, methane, and there'll be other kind of trace gases in there as well. But in effect, this syngas can be used as a direct replacement for natural gas. It will have typically a calorific value. Syngas will have a calorific value of between 8 and maybe up as far as 14 megajoules, which is very dependent and proportional upon what feedstock is presented and what's actually within that feedstock. But again, this syngas can be used within a boiler application. It can be used within an engine. And with that in mind, given the gas conditioning process that PGE employs, the gas is considered a end of waste. So even regardless of the material being presented in the form of an RDF material, it can, as a result of the thermal treatment and as a result of downstream conditioning in the form of thermal cracking and gas washing and gas conditioning, you now have converted this waste material into a very usable syngas that's comparable to natural gas and is no more polluting than a natural gas when used within a combustion system. So I know from PG's perspective, direct generation of electricity is preferred, where we go from the feedstock through the process system, through the gas conditioning system, directly into gas storage, which then automatically feeds then into kind of an engine that pulls from the gas storage system. So that enables a full waste to energy generation whilst simultaneously extracting char and carbon. So again, it's under certain conditions, particularly using SRF material or RDF material, you're effectively a carbon neutral or carbon negative application. And so again, that is quite appealing to a lot of industry. And again, I suppose when you map that particular application with efficiency, emissions, visual impact, gas quality, I suppose what PG are promoting is a system that is a climate technology solution for waste management in a carbon efficient manner. And again, that's something there that PG have developed over a number of years. And with that in mind, I suppose PG has a kind of a flagship project that they've used at a commercial scale or a kind of a large pilot scale. And this kind of reflects back then to my own experience then with, an experience there that I'm bringing here to the Irish Bioeconomy Foundation, is that, this didn't happen overnight. This took a period of trialing, demonstration, testing, and retesting. Often results don't always match expectations. So there's often time there that you would have to engineer a certain solution, see how that performs, and then revisit that then depending on the performance characteristics. So what PG have executed then is a large-scale process system rated for 3 tons per hour. Currently, this is located in the foothills of the Brecon Beacons in Wales. where there's an advanced thermal treatment process there. We work very closely with the local authority, Rhondda Saintaf, again, who only actually quite recently have attended our site and again are quite happy to keep certifications going in terms of our waste processing capacity and capability. And with that in mind, here's a kind of a screenshot of actually the back end of the building, which is showing you kind of the nuts and bolts of what's the downstream on the gas utilization component. So on the far right-hand corner of the feedstock storage was a kind of a relatively small footprint, only about 30 meters by 30 meters square, where we receive in RDF on moving floor trailers. Right beside that, then we have our building, which is the advanced thermal treatment area, which comprises of the actual system, the process system, which again is another 30 by 30 meters. And again, what's important to us is that we were able to bring the equipment into this relatively compact system with a fairly small footprint. But then at the rear of this building, this is where the real kind of revenue opportunities are. So it's the revenue opportunity one is, charging for the RDF coming over the gate, coming in the gate over a weighbridge, where again there's a charge per ton applied. But similarly, then there's a meter on the power that generated prior to going back onto the grid. So there's two revenue streams coming into this factory. The gate fee and then the meter going onto the grid. So what we're looking here on the screen then is a combination of gas storage, two engine bays. Each engine or each engine block you're looking at is rated for about 500 kilowatts of engines, where we're generating up to about 450 to 480 kilowatts, subject on gas conditioning. Again, we've used this particular technology are engines that were originally diesel engines converted for gas and then specifically tuned for syngas application. So under normal conditions, if these engines were running on natural gas, there would be kind of a 4-to-1 ratio in terms of pipe work and ignition systems. Whereas on a syngas application, due to kind of the calorific value, it's usually a 1-to-1 ratio. So it's 1 part air to 1 part gas to kind of get the engines completely tuned and obviously then synchronized onto the grid. So again, when these engines are running, the good marker that we usually get is how, typically, you're looking to see how these are operating and performing and how close we can get to that 1500 RPM on a continuous stable condition. So again, we've achieved that, and that was a kind of a major milestone and breakthrough moment for PG to ensure that we can actually achieve that. So that was a kind of an important bit. And again, we've aligned ourselves with engine suppliers that have that capability and tuning capacity to be able to kind of tweak the engines to ensure that they're fully optimized using this syngas application. So sitting behind the engines, then there's switchgear and transformers, then that brings that electrical power back onto the grid. And again, that's where we meter the power going to the grid. And again, that's that second revenue stream that we receive on that. Just to the far right, you'll also see a flare system and a char extraction system. So as indicated on the previous slide, there's two components, feedstock going in, but there's two components going out, and that's that whole biorefinery, one product in, multiple products coming out, and the second product, the char product, is nothing to be it's something quite important to be not ignored. And with that in mind, we're probably extracting for every ton of RDF that's presented, we're probably extracting something in the order of 100 to 200 kgs of char, and that would be commingled with ash, with maybe inert product, and so that's an important part that we extract. And then there's potential further revenue stream for using that char. If that char can be refined and converted into a biocoal or converted into a filter media, that can extract quite an important or potential revenue stream. And then sitting in the middle of it is that flare system. So the flare is sitting adjacent to the engines and the gas storage system. And that's in the event that if there was an issue on the grid whereby the engines need to do a hard stop, you need an ability to be able to relieve pressure within the plant. And that's typically done through a flare system as a kind of emergency flare system. So that's the kind of overall delivery of a kind of a working pyrolysis system using waste as a primary feedstock. So just to kind of show you a very quick illustration, this is kind of a block diagram of the kind of process flow of actually how the actual system that PG has developed works. So again, starting with point one, feedstock comes in. There's a kind of a rotary valve system to ensure that we're bringing feedstock in and minimize any waste air injection at that particular point. Then we actually compress and deliver that material then into a rotary pyrolysis chamber. Within that system there, the waste is getting exposed to 700 degrees, generating the gas and the char product. The char then is augered out actually of the system, whilst the gas then goes on a more convoluted route of thermal cracking, washing, and filtration prior going onto a gas accumulator and prior then being delivered to an engine. But also an important aspect there that I probably ignored in the previous slides are that as well as generating gas going onto the engines, there's a portion of that gas that's been delivered back to the static portion of the process chamber. So internally there's a rotating kiln, externally there's a static kiln. And on that kiln, then we fire a number of burners with actually the syngas we just generated. And from that, then there is a certain amount of waste heat that can be captured in a steam boiler, and then a certain amount of the flue gases then are emitted to atmosphere. But because the gas that we're actually utilizing is of an end of waste category, it means that then from a planning and permitting perspective, this is a lot easier system to get through planning authorities, and particularly at this scale, where we're at less than around 24,000 tons per year, generating up to 3 megawatt electrical output. It's a very sweet spot for a lot of waste operators where you can deploy this technology and use it in a commercial application where planning restrictions or permitting is quite easily to be managed. In fact, the site that we have that we're using in Wales is adjacent there to a bog and a large motorway, where again, as a result, it's in a special area conservation. So the emissions coming from our particular process is very much has to be very controlled and monitored on a continuous basis. And yet at the same time, we're able to maintain that due to the effort and work that we put into kind of conditioning that syngas to meet that end of waste derogation in the first instance. So it's a kind of a low NOx, low emission system, whether it's coming from the exhaust of the engines or from the waste heat system on the back end of our muffler furnace. So again, that's the overall system then, Veeam. Couple of slides just showing up is that another key element to, I suppose, developing pyrolysis systems and developing kind of waste energy applications is that we have a kind of a manufacturing hub based in Tipperary. Most of the projects we're looking at are outside of Ireland. Some of them are within Ireland, but most of them are external to Ireland. So again, it's a kind of a product that we export. And as a result, these need to be on skid formats. They need to be readily maneuvered and easily transported. So again, we always try and make sure that everything that we're manufacturing is on a skid or on a platform and stays within wide load restrictions, both from a dimension perspective, but also from a weight perspective as well, trying to stay under 45 or 50 tons at least. So again, that kind of gives you kind of an overall design and thought process that goes into the overall scheme of things. So just to maybe finish up on the process stuff, I know just from a primary green energy perspective, we dabble in other areas of bioeconomy and grass refining in terms of waste management and waste processing. And so again, we have a kind of a broad range of skills and capabilities, but pyrolysis is really probably our core is our core forte, and it's something there that we continue to evolve, continue to improve upon, and again, I suppose we're always kind of open to discussions with various clients regarding their waste management requirements and how we can satisfy that in a kind of a cost efficient, carbon efficient manner by using pyrolysis as a mechanism to valorize that bigger waste stream.
Thank you very much, Son. Your slides were self-explanatory and very engaging, and it's good to like understand. And my gatherings from your slides and your presentation, like it's very it sounds to be techno-economic efficient. Like I've seen, like you're working on this project in multiple areas and using different feedstocks. So if you don't mind, like I have just a question out of inquisitivity, like to understand with the technology, like if we change in the parameters and things, how it changes. So we in Europe right now very focused on carbon emissions. So like in this using this pyrolysis technology, you're using it for different feedstocks and different kinds of making outputs. So do you think like changing the feedstock also changing carbon emission rates using this pyrolysis technology?
Yeah, absolutely. You're correct, Naveen. The pyrolysis systems and the outputs of pyrolysis systems are very much proportionally dependent upon the feedstock that's presented. And there's a number of factors that, moisture, shred size, ash content, these all have an input in terms of these all have an impact in terms of what the outputs from a pyrolysis system. So in terms of feedstocks, obviously, there's forestry and agri residues of a kind of woody biomass fibrous nature are an ideal component for generating biochar, and where I suppose the syngas is a byproduct of the biochar production. And with that in mind, yeah, absolutely, that biochar, depending on the carbon content, depending on of the feedstock, is going to produce a variety of different carbon types and characteristics, and obviously temperature also has quite an important input. So that the higher the temperature, the more volatile is extracted, the more porous and the more pores that are within the actual process, within the char itself. And then that char, particularly if it's from virgin materials or from woody biomass materials, that can be then upgraded, if you like, then to an activated carbon, which then has an extremely higher value product, but becomes more adaptable or more flexible or more versatile for, again, water treatment applications, gas treatment applications. Again, so you can pretty much engineer a biochar or carbon to have certain characteristics depending on the input feed, and likewise on the process conditions of the actual process system and any downstream processing that may be required as well. So again, what I would say is, yeah, absolutely, a lot of input. So again, our experience is a range of everything from biomass to waste derived materials, chicken litter, meat and bone meal products. Again, all these particular products can generate a very interesting char product, but likewise there is energy potential, and some, not all of them. Sometimes there might be enough volatiles there, so sometimes they need to be supplemented with other auxiliary or supplementary fuels to make sure that the whole system is thermally balanced.
Thank you, Son. Thank you very much. And just one more question, if you don't mind. So I understand like it's a very techno-economic efficient technique and all, and like a carbon emissions changes like with the feedstock. So are there any competitive technologies for like this thermal treatment, like other than pyrolysis, like if you're making changes in the feedstock? So are there any competitive technologies being used globally, or did the state of the art?
Yeah, but there's always kind of technology solutions, Naveem, and I suppose I would look at process as not necessarily competing, but complementary to a lot of other technologies, and particularly I'd have an avid interest in co-locating a process system alongside anaerobic digestion systems, where you can look at waste on a holistic perspective, particularly within a community scenario. Where again, if you look at kind of urban or rural communities, where again you have a variety of different waste streams, but generally these can be refined and extracting or valorizing that particular waste using a combination of biological and thermal treatment. And where the likes of a biogas and a syngas that's been generated from those can be commingled. Likewise, you know, some of the residual digestate, particularly the fibrous product, is something that can be readily fed into a pyrolysis system, and vice versa. The carbon that's produced from the actual pyrolysis system can be used within an AD system to enhance the potential methane output as well. So I would say that for me, there are a number of technologies out there. I would be reluctant to say that they're competing. I would see them as being complementary in nature, and particularly where the likes of pyrolysis and anaerobic digestion to me would go hand in glove.
Thank you very much, Son. It was very well said and like a very informative, the overall webinar and the technology. So thank you for answering and joining this initiative. And IBF, on team of IBF and the European project, I would like to thank you for this initiative, and I hope like this will be helpful for the community. So thank you, Son, once again, and you can stop the recording.